long time I don't have to make a joke about my accent because normally I present in the US. So it's very nice to be here in England today with an English accent. If there's any Americans in the audience, ask the person next to you and they'll explain what I'm talking about. So I'm here today to take you on a bit of a journey and show you what we've been doing at Hackrod for the past 3 years. We've been involved in a research project with Autodesk. But first, I want to give you a bit of context. And I'm going to give you context for the project and also for my history and where I come from. So, what if I told you in post-war America there was a recycling movement that influenced the next 50 years or 60 years of motorsports, fashion, music, and is every bit as relevant today as it was then? That, of course, would be hot rodding that took off post-war in America in the 40s in California, went on to spawn a global industry and influenced everybody from the grassroots hot rodders to the best car designers of today. So let's have a little bit of a look at the history of that, because it later on you'll see where it plays a big part of our ethos at Hackrod.
Beyond just cool, the automobile has been a cornerstone of man's ingenuity, mythology, and fascination.
You guys ready?
It magically captures the ideals of freedom and inventiveness that drove us straight into and through a remarkable industrial age. The birth of assembly lines, mass manufacturing, and the Model T Ford put a blank canvas in the driveways of everyday America. At the end of World War II, a generation of Americans returned home with a taste of danger and excitement, along with newfound skills forged by operations of the industrial war machine. Everyday life seemed to run at half speed to these young men and women. They had the power to change this. Regular cars could be stripped down to the bare essentials. And using the mechanical skills learned during the war, motors could be hopped up to deliver high performance to these lighter frames. Soon, all across America, these backyard innovators were redesigning and modifying 30 years of mass-manufactured metal to produce lightweight, stripped-down, and incredibly fast cars. Each creation an individual expression of form follows function and aggressive performance ideals.
Now let's move on and join the real speed boys of the desert. At El Mirage Dry Lake, those hopped-up cars may look like a familiar old jalopy, but their innards have been streamlined and given a shot of motorized adrenaline.
A hot rod was born. Hot rodders were the original vehicle hackers. They rescued the automobile from racing into a dull future of generic mass production anonymity by embracing deep customization and radical creativity. They drove what they wanted because they made what they wanted, and they drove fast. What started out as an unruly and dangerous form of racing on the dry lake beds of Southern California rapidly became a highly organized sport of drag racing.
Standard lap with top elapsed time on our Condeck clocks, a 9.12.
These weekend warriors worked to give their cars any advantage possible over the competition. It was never enough for the average teenage gearhead to simply be fastest. He needed to be coolest. Modifications like the chop top, big and little wheel and tire combos, and stripped down, smoothed out aerodynamic bodywork became de rigueur across America. As young people created their idea of what was cool, with easily accessible raw materials discarded in the junk piles of a rapidly industrialized nation. These mechanical innovators became leading lights in mainstream American motorsports. It wasn't long before the major motor manufacturers were mining this ever-evolving youth culture for ideas and peddling furiously to keep up with the visual language of the hot rod vernacular.
Hey, you got a bitchin' car.
Yeah, I know.
Somewhere in a place where self-taught mechanics collided with beat culture, the coolest cars on the planet were created in the garages of innovators and makers, changing the car industry forever.
So I play that because it forms a major part of my history, but it also forms the basic ethos of the company that we formed in the US. Now, I was a lad growing up in the 70s in Newcastle upon Tyne. Somehow I became fascinated with hot rods. I have no idea where it came from, but I spent that childhood playing with Hot Wheels cars rather than Matchbox cars. So imagine my surprise when 25 years later, I found myself as head of design for Hot Wheels. And in 2009, I was tasked with rebuilding the brand that had been around since 1967 and bring it to life in a way that we could make more than a toy brand from Hot Wheels. We wanted to build a lifestyle brand. So this image was the inspiration we came up with to turn what was just toy cars into a whole global automotive lifestyle brand. And the guy that I got on the phone to help me do that was a guy called Mouse McCoy. Now, he was a Baja 1000 motorcycle champion, turned stuntman, turned movie director. He had a reputation for innovative filmmaking and action. And so between the two of us, we came up with a Hot Wheels for Real campaign. And the Hot Wheels for Real campaign required us to build a lot of stuff very, very quickly, and it had to work, as you'll see.
The video is from Hot Wheels. Take a look at that.
For 43 years, this place has been secret.
When you come to this facility, this is the cutting edge.
We hold back nothing. The beginning of a whole new era.
It's a kid's dream for all of us come to life. It's man's ingenuity on a grand scale. That's the orange track right there.
The tires aren't gripping. I'm losing traction.
Team Hot Wheels. In public for the first time ever.
There have been stories and rumors in the test facility. It's time to set the record straight.
I wouldn't believe what I was doing out here.
Unconscious. Got it.
Still no sign of movement in the cockpit.
Guess there's nothing you can't do with a set of Hot Wheels.
So yes, I'm very proud of that, which is why I still show it. It's really just a good way to start a presentation. But the reality of it was, it formed a new idea in our heads. The Hot Wheels test facility was a mythical place where anything a child could imagine would come to life. And that was a very interesting idea to us. But secondly, through 4 years of doing that, we realized we were using very old technology. We were really pushing the limits of how fast we could work with tried and trusted methodologies, and we were beginning to see the world of digital design and manufacturing changing. Now, a couple of years later, I decided to leave Mattel to look for something new, and Mouse was working on a project inspired by this that he called Autonomy. Autonomy was his next big movie, and his vision was the biggest car movie in the world that talks about the coming problem when driving is outlawed and autonomous cars take over. Now, if you're like me and Mouse, we like to drive cars. We know autonomous cars have a place, but we're fascinated by the notion of what happens to all those people who live to ride motorcycles, or perhaps live in the countryside, or perhaps they just love driving, and the conflict between autonomous vehicles and hot rods and sports cars and motorcycles leads to some pretty big problems. Certainly in a town like the US, where if you tell them you're going to take their guns away, they get very upset. But imagine what happens when you tell them you're going to take their pickup trucks away as well. So the tagline is, when driving is outlawed, only outlaws will drive. And Mouse came to me and said, dude, we've got to make this movie, and we've got to have the most cars you've ever seen, and all those cars have to be completely new. And of course, we need a lot of cars. So the task at hand was, how do we develop piles and piles of cars, all of which have to look truly unique and fit in with this near future vision of the transformation of industrial design, where generative design and 3D printing become a very real way of making things. And not only that, it's going to democratize the way things are made. This is when we started getting very excited. So we were invited to Autodesk for some kind of like share cool stuff night they did, and we walked in the door, and because Mouse is a big movie director, we got to see behind the curtain. And what we discovered was a fascinating world of technology coming together that hadn't quite touched, but we immediately had a vision of the future. That when you have all of these converging technologies like cloud processing, virtual reality, reality capture, generative design, machine learning, and additive manufacturing, what happens when you put them together in a way that allows anybody to build anything? At this point, we're still in like movie research mode, but after talking with people, we eventually came to this slide. Now, you may well have seen this slide before, but this slide really, for me, formed the start of my new world, my new life. When I saw not only the optimization that generative design can give you when you try to build a structure and optimize for lightweight or for strength or whatever you might want to optimize, I also saw a new aesthetic. And this is going back about 3.5 years ago now. And Mouse and I looked at each other and went, dude, because that's how we speak in California, dude, can you imagine what it would look like if we built a car chassis like that? And so suddenly, our quest for movie research took on a slightly more immediate world, and we found ourselves slipping into design and manufacturing and kind of researching the reality of where that world's going to go. Now, if you're making a movie, you've got to have a star. So Mouse and I designed the car that we wanted. We were like, if we're going to do this, let's design the car that we know we can't have. So I'd like to introduce La Bandita. It's a car that wears its heritage on its sleeve, but is going to be built with the very latest technologies. We were inspired by vintage Porsches and vintage Ferraris from the 50s, where they're amongst the most beautiful cars ever made, and I don't think anybody would dispute that. But really, when you look at them, they're just a metal upside-down bathtub with a big engine and some crude suspension. They're very simple. They're made for one thing, and that's for driving fast and dealing with the harsh realities of a road race like La Carrera Panamericana or Mille Miglia. So we set out our store and we started the design. Now, using tools like Fusion, Autodesk's kind of core new digital design platform, we realized that we could very, very quickly go from a rough sketch to a fairly complex body form. Now, my designer, Fraser, built this digital model very quickly. He had he did these sketches. So traditionally, his world would stop with the middle sketch, and he would hand it over to someone who could model and surface. But we sat him down in front of Fusion, and within a couple of weeks, he was good enough to form the car that he wanted. So already we were beginning to think, holy shit, this is a lot easier than it used to be. This didn't require 4 years of studying Alias to try and kind of surface a car. And for us, it's good enough. We're not talking about competing with the OEMs. We're talking about a bunch of dudes trying to build the car of their dreams in their garage. So we had out of form. And this is where, at the time the project was called Dreamcatcher, this is where the generative design side of things comes in and becomes very interesting. Traditionally, you would lay all your components out and you would build models and you would draw stuff, and then you would get to kind of surfacing and you would go back and forwards until you built your entire package. But what the guys at Autodesk told us, they were like, if you set your external void and then tell us what structure you want inside of it, set your goals and constraints, you can let artificial intelligence do the rest. And we were like, really? Sounds kind of rad, let's have a go at it. How are we going to do that? How do you set your goals and constraints? It's one thing setting your goals and constraints for a milking stool, where it's very, very simple structure. But when you want to design a sports car that's going to be competitive, that's a complex thing. So we looked at the world of reality capture, and we began with a chassis we already had that we knew was a good chassis. For the Hot Wheels project, we developed a lightweight sports car chassis with some off-road engineers, and these guys we referred to as the wizards of chromoly. They were the guys who could just chalk out a chassis design on the floor and fabricate it. And we knew this worked because some of the best drivers in the world had driven this car up a mountain and came back saying, that was the most fun I've had in years. So we knew this structure was good enough. So we scanned the structure captured all the hard points for suspension and engine mounts. We sensed that car up, we put Mouse in the driving seat, there was no slouch behind the wheel, and he took it out into the desert and absolutely thrashed it. Now, we weren't ever going to drive this car like this once we finished it. We're not designing an off-road car, but we figured that if we can make it survive the rigors of driving in the desert like this and capture all the data that we did with a simple loom, we partnered with National Instruments and built a simple sensing loom for all of the key stress points in the chassis. We knew that we would have captured, not only with the reality capture side of things, the geometry that makes it work, but we would have also captured all of the forces that the car went through when it was being absolutely thrashed to the limit. We had some fun closing some streets down in Long Beach. It's the benefit of having a movie director as a business partner. You get to play with all sorts of big movie toys and feel like you're in Hollywood all the time. We also scanned the mechanical components. We decided actually that we were going to make this car fit for the 21st century, and so we looked to Tesla for power. We decided that that elegant 50s looking sports car was actually going to be powered by Tesla. We didn't go to Tesla knocking on the door. We decided to put the hack in Hackrod into play, and we went to the junkyards of California, where, believe it or not, there are a lot of very cheap Teslas. Now, Tesla is a really fantastic car, but it's still driven by humans. And when you put a very fast car in the hands of humans, you tend to find a lot of them in the junkyards. So we pulled the motor out of a Tesla, and we scanned that as the major mechanical component, and we fed all of this information into Dreamcatcher, and started on the process of generative design. Now, the way it works is this. You build a digital model, and you put in your mounting points that we'd scanned and captured from the original chassis. You put in your mechanical needs, your mechanical components. You put in voids where you don't want the chassis to grow. And what's left is the area of the car within the outer shell that you want to build your structure. The wonderful thing about Dreamcatcher is that it would give us hundreds of iterations. So not just one solution, but you could flick through and move some parameters until you were happy with the way the car looked. We also pulled it into some analysis software where we could check for rigidity and any problems and do a little bit of digital proof. We also put some VR goggles on and started working on the car. This is obviously just a mock-up, but the next bit, we actually started looking at this car full size in VR. I actually fitted the engine to the transmission to the chassis 3 months before we started welding any steel. And 3 months later, once we finished the chassis and I put the motor in, it fit perfectly. So we were genuinely using VR to make key design decisions well upstream of where normally you would ever have the chance to view it in reality. Now, this is where it gets interesting, because around this time, we realized there was no way we were going to 3D print a generative chassis full size for a car. We talked to all the right people, but it just appeared there was no way we were going to get there in time, and this was for Autodesk University last year. So we took a step back, and we said, well, we're missing a point here, right? We're using all of this fantastic technology and all of this new world of cloud processing and digital power, but most people today, if they got this far, wouldn't be pressing print on like $1 million parts. Most people would probably just want to weld up a chassis. So we ran another simulation with Dreamcatcher, and we specified the material as chromoly tubing. Chromoly tubing is what most off-road teams and NASCAR teams use to build their chassis. It's incredibly strong, it flexes well, and it's been the staple of American race car design for a long time. Now, we specified thin wall tubing, and we let Dreamcatcher do its job, and the model came back as 30% lighter. Now, we had to figure out how you would actually fabricate a complex structure like that, and we partnered with some other companies in California, where there's a company in Orange in California that has pioneered CNC tube bending and laser cutting and notching and serial numbers. So we ended up with a big jigsaw puzzle of tubing, literally 320 tubes laid out on the workshop floor, but they all clicked together like a kit. And so a week later, we'd fabricated a cutting-edge, generatively designed chromoly race car chassis, and when we cut it off the frame table and put it on the scales, sure enough, it was 30% lighter than the car we started with. Now the next stage with this car, and this is where we're right now, is we've got to do some serious testing to prove out that it is as strong as the last car. But everybody who's looked at it, and all the engineers that we've looked at it, have said that not only does it theoretically look stiff enough and strong enough, but it's also a lot more rigid than the chassis we started with, because of the way the forces are now spread throughout the frame. We think we've got a very, very rigid, 30% lighter chassis that also looks a hell of a lot better, because we got to play with the aesthetics. And if you notice on these photographs, it's completely asymmetric. And at first we were like, why is it asymmetric? Well, it's, well, the car isn't really a symmetric system. And when you put a driver in one side, the chassis starts reading that you've got an imbalance. And so the generative design took into account all those forces and gave us a very strange, perfectly tuned chassis to Mouse McCoy sitting in a race car. Now, this is all very well and good, but at this point, we realized that our goal really was to look back into the world of 3D printing. And in our discussions and in our quest, one name kept coming back to us, and this is a guy called Dr. Slade Gardener. Now, Slade at the time was at Lockheed Martin. He had left Skunk Works and was working in space systems, and he again and again and again came up to us as the foremost mind in America on large-scale industrial additive manufacturing. And we were told by American Makes and countless other people, if anybody can figure it out, this guy can. The goal of the project is this: build a platform so you can drag and drop your components, choose your suspension, choose your drivetrain, choose your outer shell, and then generatively grow a chassis. And then if you decide you want to change your design, start with a different set of mechanical components, a different outer shell, and then have artificial intelligence and generative design grow you a new structure that'll tie it all together. The missing point of that is we need a printer big enough to print a chassis, because a lot of these structures really are only suitable for additive manufacturing. So we called Slade up and asked him to come and have a chat with us, and after he showed us our vision, he explained to us that he was getting frustrated with all the ideas in his head, that he couldn't move fast enough, and he decided to join Hackrod as our new CTO. I'm going to let Slade do some talking now, because he's a lot smarter than me, and I want you to hear from his own mouth his vision of the future.
I'm an expert in advanced manufacturing and materials. I've spent my career inventing materials, manufacturing processes for some of the most high-speed products on this planet and off of it. I was recruited by Lockheed Martin Aeronautics to work in the Skunk Works. I worked in a group that was specifically focused on advanced manufacturing concepts. We were called Project Lightspeed. And we were going to change the paradigms of manufacturing. And my project to enter that group was to study and to determine how we were going to 3D print the next jet fighter with carbon nanotubes. We're looking at a manufacturing future that's going to be very different. In the aerospace world, you have access to a lot of expensive but sophisticated and capable tools. Those tools are becoming more accessible. Those software packages, those imaging techniques, the analysis, even the manufacturing itself is becoming more accessible to other industries, to individuals even. And by taking those tools and offering them to more people, what we're doing is we're democratizing manufacturing. We're democratizing engineering design. We're even democratizing the quality assessment of a finished article. And all of these tools, as they become more accessible, are going to enable people to unleash their own creative and innovative desires. But there's something else that's happening that's very powerful. We're digitizing everything. We're digitizing chemistry, tolerance, measurements, quality, mechanical strength. And once these data become digitized, they can be fed to machine learning systems. And machine learning can beat the world's best chess player. It can beat the world's best Go player. Machine learning can design the world's best complex mechatronic system, no matter what it is, if it has enough data. And what we're doing right now is we're generating the data, the digital inputs that the machine learning systems are going to use to create the next best, optimized for specific requirements product.
I told you he was smart. So, Slade sat down with us. He was like, I tell you what, why don't we just start building the machine that we want? Slade's history with Lockheed Martin started up there on the left, where he figured out how to print satellites around conventional propellant tanks. He actually pioneered the additive manufacturing at Lockheed Martin needed to print the Juno space probe, which is the probe that currently is orbiting Jupiter. And then just before he left, he'd moved into an entirely different scale and had 3D printed the, I think it was a 48-inch propellant tank, which was certified for use on the Orion space program. So the guy came to us knowing a thing or two about large-scale metal additive. And he began to experiment with what he calls big metal additive. That's his DIY home project. And his goal was to produce a machine that could handle large-scale additive metal manufacturing, bring the cost down, improve the stability of the printed part, the dimensional stability, and also run a lot faster. Now, the machine that he's developing, most large-scale print machines will lay down about ½ pound to £1 pound per hour. Slade reckons he's going to be more in the 3 to 5 pounds per hour parameter. The object you see at the top right is a generatively designed propellant tank bracket for use. It's a military marine application, and this is the first project we've run on the prototype machine, and it ran perfectly. And so we're now in the process of building a 20-foot print bed to print large-scale components such as car chassis. And I've got a little bit of footage to show you of this machine in action. And as you can see, we started with a generative part and then sliced it. It's actually a hybrid machine, and one of the things that we're finding is the way to maintain tolerance when you're using deposition printing is to have a second head on the machine, which is a mill. And so we print a couple of layers and deck it, and print a couple of layers and deck it. And through that process, you get to maintain really good stability in a large metal part. And let the robot finish what it's doing. Now, Slade was very happy with this bracket. He felt it met all the parameters he needed. And the really cool thing, what you don't see here, is the cutting head can then come and trim the support off. It can, before it does that, it can do some finish work. If there's any surfaces that must be milled to exact tolerances, that can be done on the machine. The exciting thing is it now has a rewind button. So if the print screws up, which for years and years and years has been one of the big problems, anybody who's ever run a 3D printer, that if your job goes bad, it's in the trash to start again. Well, we now have a rewind button to say, hang on a minute, that's not right. Trim it back to where we go. Let's correct the file. Let's correct the machine and keep going. And the next phase for us really is to move on. Hopefully early new year, we should have a big bed ready and we can start printing our car chassis. Now, this is the final goal. We're hoping within the next 12 months, this thing will be a reality, that we will have a aluminium 3D printed, generatively designed car chassis that has been done using the techniques that we hope to standardize and truly democratize the idea of building your own vehicle. The idea that you could decide on the components you want, the layout you want, drag from a template the performance characteristics of the chassis, let generative design grow you a structure, and press print on a big machine so you can, in effect, design and build your own car. That, for me, almost bang on, half an hour, is the end of my story.